Section 6.1, Using Graphs and Tables to Solve Systems. In the last unit, we spent a lot of time with linearly related data, a lot of time. Now we're going to be looking at sets of linear equations called systems. So what are systems of two linear equations? So in example 1, we're asked to write a set of equations that will model the following information. So the price of product A was $20 in 2005, and it's been increasing at a constant rate of $5 per year. The price of product B was $50 in 2005, but it's been decreasing at a constant rate of $1 per year. And we want to know when these two prices of these two products will be the same. So if we define our variables and let x be the number of years since 2005, so that's kind of our starting year, and let y be the price of the product. Okay, so the price of the product depends on which year we're in, since they're changing each year. So we're asked to write a set of equations. So if we take the first sentence, we've got the price of product A was $20 in 2005, and that was kind of our starting year that we're going to let this be, and so this is kind of our starting point if we were to think of on the graph. And it's been increasing at a constant rate. And in the last section, we learned that when we have things that change at constant rates, that we know that we have linearly related data, and that there's a linear equation that describes the relationship between those two variables. So in this case, if y is the price of the product, so y is the price, it started out at $20, and it's been increasing, so we're going to add on $5 every year. So we need to multiply this by the number of years since 2005. Now the price of product B was $50 in our starting year. So this is kind of like our starting point. But it's been decreasing at a constant rate of $1 per year. So again, here's those words, constant rate. And so again, if we've got variables changing at a constant rate, we know we have linearly related data, and so we can write a linear equation to describe the relationship between those two variables. So the price of this product started out at $50, and it's been decreasing, so we're going to subtract $1 every year. $1 per year. So we're going to multiply by x, which is going to be the number of years since 2005. So here we have what's called a system of equations. And we've got two equations that are used to describe some information given in the same problem. So example 2, we're asked to write a set of equations for some different information. So a poster for a film needs to have a perimeter of 300 inches, and it also needs to have a height that is 4 times its width. What are the dimensions of a poster that meet these criteria? Okay, so perimeter, peri means around. So perimeter, we've got the distance around, and if we think about what a movie poster looks like, and we'll call this x and y. Okay. And so again, we need some variables, so we're going to use x and y. So x will be the height of our poster, and y will be the width, since we're asked for dimensions. So dimensions are height and width. Okay, and we're asked to write a set of equations. Okay, so the first piece of information, restriction that we had, was that the perimeter had to be 300 inches. So perimeter is, if we think about how we use that word in everyday language, like if you were told to walk the perimeter, to walk this distance around something, okay, so around our yard or whatever we have here. So if we start here and if we walk around, we're going to walk x plus y plus x plus y. So our perimeter would be x plus y plus x plus y, and is our equal sign, and that has to be equal to 300. Okay, another way to write this, if we combine some like terms in here, would be 2x plus 2y equals 300. Then we're also given the restriction that the height has to be 4 times its width. Okay, so the height we called x, and is, and then 4 times its width. Okay, so we've got our 2x plus 2y equals 300 and x equals 4y. So again, we have a set of equations where our variables are describing the relationships between height and width of this given poster. So the above examples have several linear equations involving the same set of variables in which we need all of the equations to be true to answer the given question. So like in the poster example, we needed the perimeter to be 300 and we also needed the height to be 4 times its width. So we're after an x and a y, if they exist, that make both of these conditions true. So in this section, we will be interested in knowing whether there are any values of the variables that satisfy all of the equations in the system simultaneously. So what is a solution to a system? So in this section, we will have several equations, and we want to find values of the variables that make all of those equations true. So in the last unit, we dealt with just a single equation. And so a solution to an equation were values of the variables that made that one equation true. And to solve an equation meant to find the values of the variables that made that one equation true. So in particular, the solution to a linear equation that had two variables, let's call them x and y, was the set of all ordered pairs, x, y, that made the equation true. So these definitions are slightly different for this chapter because now we're looking at a system of equations, a set of more than one equation. So solutions will be values of the variables that make all of the equations in the system true, and solving will entail finding the values of the variables that make all of the equations in the system true simultaneously. So again, in particular, the solutions to a system of linear equations in two variables will be the set of all ordered pairs x, y that make all of the equations in the system true simultaneously.